So chapter 4. So today we're going to be learning 3 major skills. The first of which is balancing equations. The second of which is reaction stoichiometry. And the third of which is not listed here, is the intricacies of oxidation-reduction reactions and how to determine the oxidation state of really any element in a chemical reaction or even just a compound. So we'll go over what that means. So first, we want to talk about chemical reactions in general. Now, chemical reactions, there's many different types, and the general definition is the rearrangement of any atoms to make different substances. That's how basic it is. So in any type of reaction, and we talked about the differences between physical and chemical changes in chapter 1, and this kind of ties into all chemical changes. So we're not including things like melting or boiling where you just change the physical state. We're talking about things like rusting, which is a form of oxidation we'll talk about later, but burning, tarnishing, baking different things, anything where you're putting in energy or doing some kind of either chemical or thermal energy where you're breaking apart bonds and making new bonds, or just breaking apart bonds and not making any new bonds, or taking other elements and making one big structure. So anything that changes the chemical nature is a chemical reaction. So in a chemical reaction, there's 2 parts. There are the reactants and there's the products. And usually all the time, the equation's written like this, where you have the reactants on the left side and you have the products on the right side. And the reactants or products could be more than one. It could be 1, it could be 7, whatever. It could be 7 things added up to make one thing. Really no rules with that. So that's something that is important and very basic about this. All right, so the chemical equations, you've noticed, maybe you've seen these in the past that are in high school, where they have these coefficients sometimes that are in the front of different reactants or products. These coefficients are what we need to add to an unbalanced equation to make it balanced. So what I mean by balanced is that every element and number of atoms of that element on the reactant side of the equation is equal to the same number as the product side of the equation. So that means, let's look at this equation. This is the combustion of methane. And we are fairly familiar with combustion reactions already from the empirical formula questions you have on your exams. So you have some organic material, in this case it's methane, and we're adding O2 to create CO2 and H2O. Now, let's just count the atoms on the left side, or count the type on the left side, and compare it to the right as we go through it. So for methane, you have CH4. So you have 1 C on the left. Look over to the right, we have CO2. There's 1 C right there. That's good. H4, so we have on the right side 2 of H2Os. So we have 2 times H2. That's H4. Nice. And then the last thing is oxygen, and we see that's equal as well. We have 2 O2, which means there's 4 oxygen atoms on the left. And then we have CO2, which accounts for 2 oxygen atoms on the right. And the remaining 2 come from 2 H2O, which gives us a total of 4 oxygens on the right and the left. So this is what we mean when we're talking about a balanced equation. One more thing is, you notice that little parenthesis G, right? That just means the state, the physical state. In this case, they're all gases because we are talking about combustion of gases. And the water is even in form of water vapor, which is a gas. And CO2 is obviously CO2 gas. But you could have solid, because that's a parenthesis S, and you can have liquid, parenthesis L. But more commonly, you're going to have parenthesis AQ, which is not written here, but I'll draw that. I'll write that. So parenthesis AQ, and that means aqueous. So once we talk about solutions in chapter 5, this will become more apparent to what that means. But basically, an aqueous solution is where you have something that dissolves in water. So the base, you ever heard of things that are water-based? That means they're in an aqueous solution. So the base, or the main solvent in that solution, is going to be water, and you have certain things, minerals, salts, different things mixed into it. So if you have a reaction that takes place in aqueous solution, that means this entire reaction is happening in a water-based medium. Whereas if it's happening in a gas form, it's happening in a container that's maybe a vacuum-based media. So that tells you a lot. Also, you can have them reactions as a solid as well. So I think I said that already, but yeah. Okay, so the easiest way, so now that we're getting into the balancing right now and how to put these coefficients into the correct place, there's really, I think in the video, I made a video last year or last summer going over in detail, very concise video, and I'll post that on Canvas, going over how to balance I call them 4 types of equations, but I don't know how I got 4. Now I'm thinking about it, I think there's only 3. But basically, there's the easy ones, there's the ones that have fractions in them, which are still kind of easy. It's the same exact approach. You're just multiplying the end product by a whole number to make all the coefficients a whole number. And then there's the really hard ones, which need a system of equations to solve. So we're going to go over one of those today. We're going to go over an extremely hard one today, so that if you're prepared for that, or at least you can somehow, maybe on an exam, figure it out or get really close to figuring it out, you can figure out anything. So it's going to be, this is a very easy one, then we'll go middle, then we'll go top of the line. So cover all spectrums. And I'll put that video after class. So basically the way I teach it is you go through it and you read it like a book from left to right, and then you go element to element, compare left and right, and you put the coefficients as needed. 99% of the time, except for the really difficult one, that works. So the things that you read in the textbooks, the things that maybe you've heard in the past on how to balance equations, where you have to write a chart, write the elements in the chart and cross them off and do different things. I never like that. So for this one, we have a certain amount of mercury oxide that reacts and it decomposes into mercury and oxygen gas, right? So the first question to always ask yourself, like I said before the video started, is the equation balanced? So to figure that out, you just look at the left and right side. And for this one, you can tell it's not, because you have one oxygen on the left side and then O2, one molecule of O2 on the right, which one oxygen on the left is 2 oxygen on the right, not equal. So we need to change that. So in order to change that, let's look at the first thing we read. And where we see this equation, all we see is mercury oxide. All right, so mercury, Hg. 1 Hg on the left, 1 Hg on the right. Good. Oxygen. 1 oxygen on the left, 2 oxygen on the right. That means we put a 2 here. Oh, wait, that changed something. Whenever you change something, if you see that it changed an element that you already passed by, you need to go back. So we can do that. So now that we have a 2 where this HgO is, we have 2 Hg. So we go to the right, it has 1 Hg. We're going to put a 2 here. And this is going to be your final answer. So it's always important to check your work. You cannot go wrong if you check your work. And I've even seen students sometimes completely guess, just based on like pseudo math, not really going through it systematically, and end up checking it at the end and it works. So if you get stuck, just try to guess and figure, no, what the hell, go for it. Give it the old college try. But this systematic way is a very good, successful approach to doing it. Okay, let's do next step up. That was a pretty easy one. So here we have the combustion of glucose, which is a more complicated molecule than methane, like we saw before. So we're going to do the same exact approach. So let's look at carbon. Carbon, C6. All right, there's 6 C's here. There's 1 C over here. So we have to put a 6 in front of CO2. That's exactly what you do. I can't write when it's going. Oh, I could. Okay, cool. I could do this. Nice. So you're going to put a 6 right here. Nice. So now we have 6C or C6 on the left and 6C on the right. Next thing is hydrogen, H12. All right, look on the right, H2. Okay. So we're going to put 6. 6 times 2 is 12. So that means we have 12 hydrogens on the right, 12 hydrogens on the left. So then you see oxygen. In this case, where it gets weird. So you have oxygen on 2 places on the left and 2 places on the right. So let's see what goes on. Let's just see. So you have oxygen 6, oxygen 2. That means oxygen 8. There's 8 oxygens on the left. On the right, you have 12, and then you have 6, which is 18. You have 18. Okay. So what can we do to this oxygen to make 8, or to make so if we get rid of the 6, so let's say that 6 is gone, we have 2 over here. Cancel out with this 6, we have 12. So in order to make this work, we need to make this O2 count up to the 12 remaining oxygens that are not canceled out by this O6. That makes sense. So what will go here in the O2? Good, awesome, 6. So then if you got to think about the math a little bit. So after you're done with that, once you go through it, you can see that oxygen is canceled. Oxygen is good because you have O6, then you have O12. So you're going to have O18, and then here on the right side, you have 18. Now, it is not advisable. So here's just some expert tips. If you have elements that are by themselves, those are the ones you want to go after before you change anything else. Because you can really mess yourself up if you start changing the coefficient for C6H12O6 or for H2O or for CO2, because those are kind of already set in stone. If you look at it, 6C, this coefficient has to be the exact same coefficient, or this coefficient has to be 6 times this coefficient at all times, because that's the only place on the left side where carbon is. So you have to go through this slowly when you're learning, but then you can get faster as you go along. So that's another example. So we'll do more. All right, so we'll do more. Here, let's do this one. I'm gonna take this one. I'm gonna put it all the way up here. Okay, let's do this one. Combustion again. There's combustion of butane. So we have C4, we have 4 over here, and then we have 1 over here. So we're gonna put a 4. We have 10 over here, 2 over here, put a 5. Then we have O2. All right, so let's look on the right side. How many oxygens do we have to contend with? We have 8. We're at 4 CO2, means there's 8 oxygens. And then 5 O means there's 5 oxygens, which equals 13. Okay, so then you get a little snag. You get a snag. You have to make the coefficient of O2 equal 13. Well, whatever whole number you put there, it's going to be an even number. You can't get 13, right? So what would you do? Yeah. Double everything? Yes, that'll work. But that's you inverted the traditional steps, but that'll still work. That'll still work. I like that answer. So we'll get to doubling everything. So I'll just give you the answer right now. You can force the coefficient to be whatever you want, even if it's a fraction, which is, in this essence, you're going to double everything. So let's do it both ways. So what I would do is, since I'm programmed to teach this class the same way every time, is I would put 13 over 2. Yeah. So what this does is 13 over 2 times 2 is 13. So you can kind of force it by putting in the correct fraction. And then you can check your work again, you see 13 and 13. So now you cannot leave it like this, because if this was down to the molecular level, you cannot have 13 over 2 of an atom. You can't have a half of an atom, right? So you'd have to you have to multiply the entire thing by 2, just like you said. So so the correct answer at the end of the day would be 2C4H10 plus 13O2 yields 8 CO2 plus 10 H2O. Now, if we did it the opposite, just like you said, where we can, before we put in this 13 over 2, if we doubled it, the entire equation beforehand, what would we get? We would get basically the same thing, 2C4H10 plus O2 times plus 2O2, if we doubled it, equals 4 CO2 plus, oh no, 8 CO2 plus 10 H2O. So in this case, we would have how many oxygens here? We'd have 16 oxygens on the right, plus another 10, which is 26. So we'd have to make O2, we have to make this a 26, therefore 13. So yeah, that would work perfectly. It's just the inversion, the inverted steps. So these are the medium ground, more difficult ones, not the super hard. We'll do that one next. We'll do that one, where is that? Yeah, we'll do that one here. Yeah, but, okay. Any questions on that? But when it gets a little bit complicated is when you have one element that is in multiple compounds in the reactant or product. But you just have to stick through it systematically and figure it out, just like we did here. Okay, so another thing we could do with chemical reactions is once they're balanced, we can use these coefficients as molar ratios. And that's really what they represent. That's why we do this, is that when we carry out reactions in the laboratory, we can know exactly how much mass of one of them will react with a certain amount of mass of the other one, based on stoichiometry, based on the amount of moles, and based on their molar relationship in the balanced equation. So it's not all the time where, you know that 5 grams doesn't react with 5 grams all the time of A and B, because it depends on the molar masses and the amount of moles of A and B. And even if that's true, even if they are exactly the same, you don't know that their balanced chemical equation is going to give you the same results of a 1-to-1 ratio. It's not always 1-to-1. In this case, you have, for butane, it's a 2-to-13 ratio with oxygen. So it could be anything. This is why you have to balance the equation. And this is why, and then you can use that ratio for calculations, which we'll do that here. So let's do this one. So we balanced this one already, and we can just take a look at the math. So in a glucose example, calculate the mass of CO2 produced by burning 100 grams of glucose in excess oxygen. The excess oxygen part refers to just a flame being there, or like a lot. You have an unlimited amount of flame, so you're good. So if we were burning 100 grams of glucose, and we're given this equation, the first thing we do, determine if it's balanced. And since we balanced it already, we know it's balanced. So now we can look at 100 grams, and we have 100 grams of glucose. Now, your instinct at this point, after the first exam, should be, oh, find the molar mass. If I'm given an equation with an amount of one of the reactants or products, find the molar mass, figure out the moles. I cannot compare grams to grams. I can only compare moles to moles. So we're going to do that. So 100 grams of glucose divided by the molar mass of glucose, which is 180. If you do 6 times 12 plus 12 plus 6 times 16, it's about 180. And you divide those two numbers and you get 0.55 moles. That makes sense, right? 100 out of 100 grams is a sample. 180 is the total molar mass, so it makes sense it's about half, a little bit more than half. So you have 0.55 moles of your glucose. So now the question is asking for the mass of CO2. Okay, so if we forget the amount that we're given of glucose, so we just look at the equation, the relationship between glucose and CO2, we can see that 1 mole of glucose reacts to produce 6 moles of CO2, since it's a 1-to-6 ratio. That's very important. That's really all the information we need from the equation. Because now that we have 0.55 moles, we can do a proportion, or you can think about it as cross-multiplying, whatever you want to do in math, to say, all right, 1 mole of glucose makes 6 moles of CO2, therefore 0.55 makes 0.55 times 6, whatever that number is, of CO2. And that number ends up being 3.329 moles of CO2. Does that part make sense? So that's stoichiometry in a nutshell. That's reaction stoichiometry. You're taking the molar ratios that are presented in the balanced equation, and you're using them to solve for masses. of what's going to be produced or what's going to be, what do you need to react with something? There's an abundance of questions that could be asked. So the final step, now that we know the moles of CO2 and we're being asked for the grams of CO2, is very simple. Is to just multiply by the molar mass of CO2, which is 44, and you get 146.5 grams. Any questions on that? So you're going to get, so it's good to go through, I think, on the homeworks. There should be comprehensive problems that give you an unbalanced equation. They give you a stoichiometric problem like this to sort through and to try to figure out how much of a certain substance you need to react with another substance. Okay, so let's go back to balancing real quick. Or we did this already. Oh, we did this one. Okay, so let's do another stoichiometry. So we did this one already. This is the one I copied over. This is the combustion of butane, right? So butane combustion, we have the balanced equation right here. I'll star it right there. So the question is asking for how many grams of of H2O will form from 134 grams of butane. Make sure it says that. Yeah. Okay. Oh, there's a question. Oh, yes, I'll go back. And Josh, you're right. Yeah, it should come before combustion. Yeah, because you're introduced to coefficients before you know what they mean, which is, I don't know. You could complain to Pearson for that one. I don't write the textbook. I do want to write a textbook one day. Hopefully it'll be good. I have some ideas. They're all written in different order. Even like 121, which is the other class. Same material, it's just different order. Weird, I don't get it. Okay, so how many grams of H2O will form with 134 grams of butane? So initially off the bat, we want to say there's 134 grams of butane. How many moles is it? All right, so the molar mass of butane is C4H10. So that means we're taking 58, but we're taking 4 times 12.01 plus 10 times 1.008, and we're getting 58.12. So I'll put 58.1 grams per mole. So now we have 134 grams of this butane. So we divide it by the molar mass, and we get probably a little bit less than 2, or probably about 2. So 134 divided by 58.1, you get 2. It makes sense. Yeah, it makes sense. Yeah, 2.3. 2.3. Yeah, makes sense. Okay, cool. So you get 2.3 moles of butane. Okay, so the question is asking for how many grams of H2O will be produced from that amount of butane. So let's look at the balanced equation. Butane reacts with, or to produce water in a 2 to 10 ratio. Meaning for every 2 moles of butane that are combusted, 10 moles of H2O is produced. So we can use that. If we have 2 moles equals 10 moles, meaning it multiplies by 5, 2.3 moles is X amount of moles, meaning the 2.3 times 5. 2.3 times 5, that gives us 11.5 moles of H2O that's produced from 2.3 moles of butane, C4H10. And now the question is further asking how many grams of H2O, which we've done this before, multiplied by the molar mass of H2O, and we get, which is 18. What happened to my calculator? Where's the delete? 18. You get 207. The answer is 207 grams. Cool. Which happens to be the molar mass of something. That's a molar mass of one of the elements. I forgot which one. Mercury, maybe? Yeah. Maybe lead. One of the lower ones. Anyway, point is, that's how you do it. So are there any questions on that? Okay. Okay, let's do a really hard one. So, this is what they look like. Now, to know it's a really hard one, this is the thing. Like, you're going to be on a test and you're not going to know which one. Oh my God, I just know to balance it. But what did the professor say? Which one? There's different types. Always try to do it the easy way. So try to go through it, and we'll see what happens when you go through it. Copper, there's one of them here. There's one of them on the right. We're good. Hydrogen, there's one of them here. There's two of them here. All right, fine. Nitrogen, there's one of them here. There's 3, 4. Okay, if I change this to a 4, then we need to change this to a 2 because our hydrogen's doubled. And then what happens? Then we have, what would I do? Oh, no, wait. NO3 2, meaning 2 nitrogen. Oh, did I do something wrong? 3. Yeah, okay, I meant to say 3. Thank you. I'm just testing you guys. Okay, but the point is, you could do this all day, this method, and it doesn't work. You're gonna end up going back and forth, and it's just not gonna get to the right answer. So let's erase it. Or let's just screw that. We can just go here. Question?
Yeah. Can you go back to?
Oh yeah, I forgot. Sorry. This one.
Oh, not even that. I'm already way past that. I was going back to the nitrogen thing. So. Yeah. One more. So, would there be 3 nitrogens? Because the 3 is next to the oxygen. I'm confused where you got the 3 nitrogen atoms from.
Oh, so there's 3 nitrogen on the right, and the reason why you have NO3 2, which means there's 2 nitrogens from the copper nitrate, and then there's 1 nitrogen alone from the NO.
Yeah, okay. I didn't see the NO over there.
Yeah. So when you have the same elements split up into multiple things, you can kind of tell when it's a weird equation, because when you have things are split up all the time. But yeah, so that's why there's 3. Okay, so let's go through it the difficult way. All right, so the difficult way. This works. I had one of my students in the summer, no, this was my winter class, where he did every one of them this way. And when you do the easy ones this way, it does take longer, but it's still shorter than the one we're going to do now. They're seamless. But let's do this one. So the way you do it is you set each coefficient to a variable. And you set A, B, C, D, and E. In this case, there's 5 of them. In most cases, there might be 3 or 4, but 5 is tough. So we're going to end up with a crazy system of 5 variables, of 5 equations and 5 unknowns. Mind-blowing. So we need to make associations with these variables. And we can do that based on the left and the right side, the amount of each element to start out with. So copper, A. So what do we know about A? We look at copper on the right side, it has 1 here, right? There's only 1 copper. So this means that, can we agree that for whatever A is, C has to equal the same thing, the same thing, or else it's not balanced, right? If this one's 2, the other one has to be 2, and there's no way to go around that. So A has to equal C. All right, let's look at the next one, B. And this is the best way to do it is to write down for each element. So this is for copper. We'll write down for hydrogen now. So for hydrogen, B is associated with hydrogen. So where's hydrogen on the right side? It's over here. It's in one spot. So you have 1 hydrogen on the left, 2 hydrogens on the right. This means that whatever B is, in order for this to be balanced, has to be twice as large as E, because that's the only way for B to equal, for the coefficient of 1 hydrogen to equal the total amount of the coefficient of 2 hydrogens, is if B was double the amount. So the equation would look like B equals 2E. That make sense? Okay. Next, let's look at nitrogen. And we're also dealing with B for nitrogen. So for nitrogen, we have one nitrogen again. And now we have a combination of nitrogens on the right side. So we know that B has to be all the nitrogens on the left. C, how many nitrogens are here? We have 2. So equals. We have 2 here and then 1 with D. So I'll just write out the equation. So B has to equal 2C plus D. Because whatever is on the right side, including the coefficients times or multiplied by the nitrogen amount, that has to equal B. So B has to represent the entire number of nitrogens in the equation on the left side or the right side. Does that make sense? And then the last element is only 4, right? Yeah, the last one is oxygen. So for oxygen, there should be 5 equations. There 5 equations or 4? Oh, it's 4, my bad. 4 equations, 5 unknowns. Even more crazy. Okay, so for oxygen, we know there's 3 here. So we're going to put whatever 3 times B is, it has to equal, let's see how many oxygens are on the right. We have 3 times 2, which is 6. 1 here, which is 1. And then 1 here, which is 1. So whatever 3B is, the entire amount of oxygens in the left side has to equal 6 times C plus D plus E. Plus D plus E. Did she set that up right? Yep. Okay, cool. Okay, does that make sense? So setting up those equations might take a minute or two. And I'll tell you right now, now that we're online, I highly doubt you will get one of these on the exam because they'll take 5 or 6 minutes to do. Unless it's an entire open-ended, like one big open-ended, I don't think so. But it's good that we're learning it just so you know how to do everything. Okay, so now let's start solving away. Now we can put, there's many different ways to approach this, but one's easier than another. So you can think about it all day, but let's do something. Let's put this 2E into this B, right? B equals 2E. We have B equals 2C plus D. So we'll put the 2E over there. 2E equals 2C plus D. And now we can solve for D. So let's solve for D and get another expression. D equals, what happens is we subtract 2C from each side and we get 2E minus 2C. And you could be like, Professor, why are you doing that? Can't you do something else? You probably can, but this is the way I'm doing it. This is the way I rehearsed it. Watch, I'm still going to get it wrong. Because when the first time I went through this in a live class, I was thinking of 5 different ways to do it at the same time, and I couldn't articulate it, so I was confusing everyone. So let's just pick one way and stick with it. Okay, so we have D equals 2E minus 2C. All right, so let's put that D into here. So we could do that. And also we could put B into there. So what I'm doing is, the approach that I'm doing is I'm having a big equation that has a relationship between E and C. Why am I doing that? That's the first thing I thought of. Math, that's why. So we know that B equals 2E, right? So we can put 3 times 2E, which is 6E, equals 6C plus our new D, which is 2E minus 2C plus another E. So now we have this big thing of E's and C's, and we can easily condense it. So we have 6E equals, that would be 4C plus 3E and then we convert that. We subtract e's to both sides, and then we get 3e equals 4c. That's great. That means if we solve for either one of them, we know that, so if we solve for this, we solve for c, we know that c equals 3 over 4e. Or if you look at, there's many ways to solve this in your head. Basically, just if you look at 3c equals 4e, you know that the simplest answer is e has to equal 4 and c has to equal 3. That's the simplest way for this to work. And the way they represent it is you can manipulate this equation to get this expression right here. The ratio between e and c is 4 over 3. I know this is tough, but you can, once you get that association, that's basically it. All you have to do is plug and chug. So any questions up to this point? I don't even know if I can answer any questions. It's just you gotta do it. We're showing you how to do it. But if there's anything that's outstanding, I'll answer it. Okay, so I'll just keep going. So once you know that e equals 4 and c equals 3, let's do this. So we can figure out a immediately, right? And we can figure out b immediately. So we know that c is equal to 3. That means a is equal to 3. A is equal to 3. We know that e is equal to 3. E is equal to 4. B is equal to 2 times e. So 2 times 4 is 8. So b is equal to 8. Just make sure I'm correct so far. Yep. Okay. Because the worst thing is to mess this up and not know where you're at. All right. So now we have 4 out of the 5 variables. So now we can solve for d. And we have an expression for d right here. So d equals 2e minus 2c. So if that's the case, then d equals 2 times 4, which is 8, minus 2 times e, which is, or sorry, 2 times c, which is 3. 8 minus 6 equals 2. So then we have c equals 3, d equals 2, e equals 4. So then we're done. That's craziness, right? So yeah, so after that's done, you can put the answer in, and you'll get, I'll let you write it down first. But yeah, this is insane. Like I said, I don't think there will be one on your test, but there may be on your homework, and it's also very good to know. Because in my undergrad, I didn't learn how to do these. And so Stevens doesn't learn it. Maybe Rutgers doesn't learn it. I don't know. But most schools don't learn this way. So it's really good to have a good tool to have in your back pocket. All right. So let's move on to the answer. Once you put everything in, you get this. So 3C, and you can always check it at the end, and it will work out. So the answer's on the bottom. Okay, cool. So let's move on. All right. So let's do this one. Oh, the answer's there. Okay. Well, bye. All right. So let's do this one. Just more practice. Okay, so C6, there's 6 there, there's 1 here, put a 6. There's 14 hydrogen here, there's 2 here, put a 7. 2 oxygens here, now we have 12 plus 7 is 19. So we can force our fraction, or we can multiply it by 2, and we can put 19 over 2. So if we put 19 over 2 there, and multiply the entire equation by 2, what do you end up with? You end up with 2C6H14, which is hexane, by the way, plus 19O2 yields 12CO2 plus 14H2O, like so. Okay, cool. Those are combustion ones. If you keep repeating them, they'll get quicker. Yeah. Okay. Any questions? No. So hopefully a lot of you guys did watch my video from chapter 4. Is there a cap on how high the coefficient could be? The answer is no to that. But if you find yourself constantly changing them, and it constantly gets higher and higher as you go back and forth, you're doing something wrong. They shouldn't go that high. And your process should maybe you should probably, at most, in a really difficult one, go through it once or twice. If you need to go through it 3 or 4 times, crossing out coefficients, putting in more, chances are you're doing something wrong. And I'll show you an example of that. Okay, so here's the example. Now, practice on your own. Actually, you want? Let's do this on your own. So I'll give you guys like 5 minutes. I'll give you guys until 7 o'clock sharp. For an acid-base reaction, it makes water. So that means the best way you need to split up water, because the components of water are hydrogen and OH and hydroxide. So water is actually hydrogen hydroxide, HOH. And that's why water is neutral, believe it or not, because hydrogen is something that is, we learned about naming acids, right? So hydrogen is something that is intrinsic of acids. They have a hydrogen and they tend to dissociate when they put in solution. And bases tend to have hydroxide, at least the strong ones do. Some of the strong ones do. And that's something that's associated with bases. So once you add the hallmark for acids and the hallmark for bases into one compound, you get something that's completely neutral. And that's why water is neutral. It's composed of the acidic component and the basic component put together. So the best way in acid-base reactions to write water is HOH. If we do it like this, let's see how the bouncing goes. And just to make it clearer, I'll rewrite the whole thing. BaOH2 yields HOH plus BaCl2. All right, so let's go to H. So here's H. There's one H here. OH is something different. OH is hydroxide. So we have H, OH, good. Cl, there's one Cl here, there are 2 Cls here. I have to put a 2 there. Now there's 2 H's. I have to put a 2 here. We're done. But let's just double check. So let's go on to barium. Barium is 1, barium is 1. OH is 2, OH is 2, 2 OH. Done. So if you split it into water, it becomes insanely easy. It becomes one of the quick ones. If you split up water into HOH for an acid-base reaction. And how do you know if it's acid-base reaction? Well, if you see something with an H in front of it, added to something with an OH in the back of it, and the product has water in it, then it's definitely acid-base. So, and some kind of salt. So like barium chloride is a salt. Yes? Doesn't matter. But let's say on a test, right? Since you're taking it online, they have H2O written down. On your paper, translate it to HOH, figure out the answer, put the coefficients back in, as they should. So yeah. And HOH is completely right. I mean, I wouldn't mark it wrong. Okay, cool. So let's move on. We've been on this one for a while. All right, so we're going to learn a limiting reagent, and then we'll let's just blast through this. So we understand the molar ratios, what they mean now. We understand that it's the stoichiometric ratio of how they react to make a certain amount of products. So in this equation, you have the combustion of octane, C8H18, to 25 moles of O2. 2 moles of octane react with 25 moles of O2 to make 16 moles of CO2, 18 moles of water. So that's the stoichiometric ratio. And we can use that ratio like we did before to our advantage to figure this out. So if, for example, we burn 22 moles of this octane, how many moles of CO2 form? So the ratio is 2 to 16. So that means if 2 moles of, there's different ways to set this up, but I think about it very, very logically and very slow. If you're good at math and you're sharp on the ball, it's been a while since I've taken calc, so I just think about it very simply. If 2 moles of octane make 16 moles of CO2, then 22 moles of octane make X amount of CO2. So a simple logical proportion like this. And you come to the conclusion that the ratio of octane to CO2 is 8, meaning 16 of CO2 to 2 of octane. So 16 over 2 is 8. So you're multiplying the equation, or multiplying the amount of octane by 8. So you'd get from 22 moles to 176 moles. Or you can do kind of like a unit conversion where you have 22 moles of octane. You know that 16 moles of CO2 reacts with 2 moles of octane. Moles of octane cancel out. Do the math, you get 176. That's the best way to do it, actually. So you don't overthink yourself. Cool. So that's basically stoichiometry for you. But now let's talk about limiting reactant. So in some of these equations, you're going to be given 2 amounts of reactants. So let's say there's 2 reactants. You're given 5 grams of one, or 5 grams of A reacts with 7 grams of B. How much of C is created? That'll be a common question. And to answer that question, you need to figure out which one, either A or B, runs out first. So you can't assume that A and B are going to totally react perfectly together and there's going to be none remaining. Since this is a laboratory kind of experiment, there's always error. You're not really aiming for a perfect reaction. One of them is going to be in excess. Just like if you're burning something, the flame or the O2 is always going to be in excess. There's going to be an abundance of it as much as you need. And usually the thing that you're burning is the limiting reactant. So the same thing applies here. We got to figure out which one is the limiting reactant. And this pictorial representation of limiting reactant sums it up pretty well. Where if we're reacting methane and water to create these little packets right here of the 3 H2 molecules in the CO. If you have too much of water, the remaining waters that are in excess just won't react, and they'll just be left over. So then, if that's the case, the methane, the CH4, is the limiting reactant, because if there was more of it, more of the H2O would react. So it is limiting or stopping the reaction because it runs out first. So that's what we're figuring out for these questions, is which one runs out first. And we can do that based on the stoichiometry. And really the key is based on how much that each reactant is destined to produce of a certain product. So the way these are going to go is we'll just go to an example, but then we'll talk about it. But then, yeah. So this is what the question looks like. You have a vessel with 300 grams of water, 250 grams of methane. What is the limiting reactant? How much CO is produced? Sometimes they won't even ask you what's the limiting reactant. Sometimes they'll just ask you how much CO is produced. In that case, you would need to know, all right, to figure that out, I need to know which one runs out first. And then I use that one to figure out how much CO is made. Because you can't use the other one, the excess, because not all of it's going to react. So you don't know. And then the cool thing about stoichiometry, you can actually figure out how much is not going to react. So if you were to do a lab experiment, you could figure out how much of the other one I need to add to get a perfect reaction of everything to mix. So there's a lot you could do with stoichiometry. It's very powerful. So the flow through of how we solve these problems. The first thing you're going to do is obviously figure out moles. First thing is always the mole. Well, first thing, really, the real first thing is it balanced? The second thing is mole away. Just get all the moles, every number, right? Then figure out of the moles of the reactants, which one independently would correspond to the most product. Whichever one corresponds to the most product is not limiting. Whichever one corresponds to the least product, that means when it's used up, it makes 2 moles, for example. The other one, let's say, makes 3 moles when it's used up. The one that makes 2 moles is going to be used up first. Therefore, it's limiting. And that's the one you need to use in your calculations for when you determine how much of the product is going to be produced. I think I summed that up pretty well. So let's get started. Now, let's write things. Nah, we can just do it. It works right here. So I'm being lazy. But all right, so you have the 300 grams. Let's make sure it's balanced. So CH4, we have a carbon here. We have a carbon on the right. We're good. Hydrogens, we have 4, 6. Hydrogens here, we have 6. Oxygen, we have 1. Oxygen, we have 1. Good. Next, you have a vessel of 300 grams of water. Off the bat, 300 divided by 18. Figure out that moles. That's exactly what they do. And they get 16.5 moles of water. Then 250 grams of methane. Off the bat, boom, divided by the molar mass of methane, which is 16. Since 12 plus 4. So you do that and you get 15.6 moles. All right. Now, some students make the mistake of, all right, I have the moles. CO is a limiting reactant because it has less moles. That's not true. It's determined on strictly the amount of product moles that the reactant is responsible for. And another good question is, all right, we can figure that out using the ratios, which is exactly what you're supposed to do. But which product do we use to compare it to? H2 or CO? In this case, it would be CO because the question is asking for that. But if the question didn't ask for that, if the question just asked, what's the limiting reactant? Which product are we going to use to compare it to? Anybody know the answer? Boom, doesn't matter. Honestly, the answer is whichever one has 1 as a coefficient or the most simple coefficient to work with. So it doesn't matter because either way, you're going to get the same answer of which one runs out first because it's the same reaction. So we can do that. And what do they say? They said methane's limiting. It just so happens to be limiting, not because it has less moles. So let's figure out why. So if you look at the ratio, let's go methane to CO, right? Because H2 has a 3 in front of it. We don't want to deal with coefficients if it's easier. And also the problem asks for it. So it turns out that methane is in a 1-to-1 ratio with CO, meaning we have 15.6 moles of methane. So it corresponds to 15.6 moles of CO, okay? And it turns out this is very simple. We also have a 1-to-1 ratio of H2O to CO, which means this 16.5 moles of H2O corresponds to making 16.5 moles of CO. So the CO2, or sorry, not the CO, there's no CO2. The CO, the carbon monoxide, will correspond to the least number of CO moles when it's fully reacted, meaning it is the limiting reactant. So we know that, check. So now we can figure out how much CO is produced from that. So you take the moles of CO that we know is produced, multiply by the molar mass, and you get a number. You get 437 grams of CO. Follow-up question could be, and we'll do this on a separate slide. Copy that. Oh no. Click the wrong button. Okay, a follow-up question could be, how much H2 is produced? For that one, we're not going to do the math on the screen, but we're going to do, we can just look at the ratio. We can see that methane is methane and water both have a 1-to-3 ratio with H2. If that's the case, then since methane is the limiting reactant, it will make 3 times the amount of H2. And since we have 15.6 moles of, let's just say, oh, this is whatever, but you get my point. Luckily, it's a 1-to-1 ratio. This math makes sense, but there's a typo. This should be, the H2O should be CO. Yeah, but it's a 1-to-1 ratio. Okay. Anyway, so regardless, we know that we have 15.6 moles of CH4. We know that. So if 15.6 moles of CH4 corresponds to 3 times that, or about 47, right? 46.8 moles of H2. That's how much H2 is made. We can also figure out, a good question would be, how much of the excess is remaining when the reaction is completed. And we can figure that out. We can look at the amount of both reactants and see what ratio they're in. And they happen to be also in a 1-to-1 ratio, because this is an easy problem. Now, them being in 1-to-1, we can say that, all right, when methane's done, it uses 15.6 moles, all of it. Same thing for H2O. It would use 15.6 moles because it uses all of it, or it uses all the same amount as methane does. So the difference of that is, I could do math, 0.9. So the difference to that of the moles of H2O and the moles of methane is 0.9. That means 0.9 moles of water will be left over. So you can figure out all that information. It's okay if you've lost me in the last couple of steps, but you can figure out basically any type of information from the stoichiometric equation. It's very powerful. So it's important that you know how to manipulate it and you're comfortable going back and forth, using the ratios from moles to grams and all that stuff. So it'll make it very easy for you to manipulate these equations. Okay, any questions? No? Okay. The next is limiting reactant and yield. So in an experiment, in an actual experiment, you are not going to yield everything that you calculate in the problem because you're going to spill some, you're going to, the air, atmosphere, whatever, you don't weigh it out correctly. But there's always a percent yield. And this percent yield is based on what you actually yield from the experiment divided by the theoretical yield, which you're supposed to get. The theoretical yield is really 100% of the product. And the percent you just divide it by 2, multiply, or divide them together, and then multiply by 100. So sometimes in an experiment, which maybe hopefully by next semester will be on campus fully, where you can actually do some labs, and you'll see sometimes you might get a percent yield that's higher than 100%. Usually in organic chemistry, you get that. And you're like, oh, how's this possible? Well, because what you're holding is not fully, not all the product. If you're doing this reaction in a mixture with a solvent, maybe the solvent didn't dry out. If you're using it with water, maybe there's still water in there. There's a lot of possibilities that could make the weight of, or the mass of your yield be more than the theoretical yield, because it's not just your product. There's more stuff. There's more contaminants in there. So for something like percent yield, we'll do a very quick example where we had the methane plus water example from before, and let's say the actual yield was 337 grams. What is your percent yield? So the theoretical yield we found was 437. So this whole reaction, we know that methane's limiting, and it would produce 437 grams of CO. If that's true, then we would do, the actual yield would be 337 in this case. Maybe he spilled some, divided by 437, that's 77%, 77.1. So that's a pretty good yield. Some experiments lose so much and use so much energy to the atmosphere, or the container, or other parts of, or the byproducts, that you sometimes get 20% yield, and that's considered pretty good. It depends on the reaction. For simple ones like you'd get in Chem 1, everything should be around 100% yield, theoretically. But sometimes the theoretical yield is actually low because this is the way the reaction works for some complicated organic chemistry ones. Okay, so let's do this one from the homework. This is from the Moodle homework from last year, but I'm not sure if it's there, but it kind of encompasses everything. And then after this, we'll go to redox, which is oxidation reduction. And then we'll talk about chapter 5 for like 10 minutes, and then we're done. So we'll probably leave a little bit early. But if you have any questions, you could ask in the meantime. So anyway, let's do this one. Let's do this big comprehensive question. Okay. You have a reaction between chlorine gas, Cl2, and P4 to make PCl5. What is the percent yield? That's a loaded question. That's saying that you need to find out the equation, balance the equation, figure out the moles of all the reactants, figure out the limiting reactant, figure out how much of the product the limiting reactant is responsible for making, and then take that number and put it over the actual, or put it in the denominator of the actual yield of 3.64, and then figure out the percent yield. So this encompasses every skill we learned so far. So good metric. And don't worry, I don't think all of them will be like this on the homework. So Cl2 plus P4 makes PCl5. All right, so let's do what we do best, is doing this, is doing the balancing. So Cl2, Cl5. Put a 2 there, put a 5 there. Nice. P4, 2P. Okay, let's put a 4 here. And then if we double that one, we can double this one. Done. Yep, that works. Cool. So let's rewrite it. We have 10 Cl2, which means there's 20 Cls, plus P4. It would, yeah, plus P4 yields 4 PCl5. You have 20 Cls here, 20 Cls here, 4 phosphoruses. Cool. All right, next. The reaction of 9.32 grams of Cl2 with 2.2 grams of P4. Automatically find the moles. Let's do that. So we'll do 9.32 grams of Cl2 divided by 9.32 divided by 35.45 times 2. 35.45 is the mass of chlorine. 35.45 times 2. That gives us 0.13 moles. And then we'll do the same thing for P4. So we have 2.2 grams of P4 divided by the molar mass of P4. Who wants to give me that? I think, what's phosphorus? 31.9 or something? Could be prepared for this. Let me see. Oh, nice. 30.97. So I'll just put 31. 31 times 4, 124. So 2.2 divided by 124. That's 0.017. Nice. Okay, cool. And this is moles of Cl2, moles of P4. All right, so now let's figure out how much of the product each one of these moles corresponds to producing. So you have, based on the ratio, 10 Cl2s make 4 PCl5s. So let's write that ratio down. So 10 Cl2s make 4 PCl5s. We have 0.3 Cl2s. So we're going to multiply 10 Cl2. Oh, no, we're going to divide that. Where's the eraser? Oh, no. Draw. There we go. At least she's black. And we'll stick with red. All right, so using the conversion factor, we have 4 PCl5s over 10 Cl2s. Cl2s will cancel out. You get 0.13 times 4 divided by 10, and that equals 0.052 moles of PCl5 produced from that, producing the Cl2. Or sorry, producing the Cl2. Now let's do the same thing for P4. So you have 0.017 moles of P4. And we know from the equation that 1 mole of P4 corresponds to 4 moles of PCl5. So we could just multiply it by 4 to figure out the amount of PCl5. 0.017 times 5 equals 0.085 moles of PCl5 from here, from there. Yeah. Okay. So now we know that the one that creates the least amount of moles is the Cl2. Therefore, it is the limiting reactant. It is corresponding to 0.05 moles of PCl4, where the chlorine is corresponding to, where the P4 is corresponding to 0.085, which means it'll be in excess. Now, this is a great question because the initial moles that you calculate of both Cl2 and P4 are not indicative of the answer. The Cl moles had 0.13, which is a lot, compared to the amount of P4, which is 0.017. So some students would be like, oh, just because, yeah, this one's less, it's probably going to be limiting, right? But the answer is it's not, because you have to factor in those ratios. And one of those ratios is a 1:4, the other one's a 10:4. So one got reduced by double, the other one multiplied by 4. So it'll make that difference. Okay, good. So now after this, we're not done, because we need to figure out the amount of product in grams determined by their full reaction with the limiting reactant. So the limiting reactant we said was the Cl2, since it produces less moles of PCl5. So let's multiply that number. Let's take it up here. The 0.052 moles of PCl5, PLC5. Wow, I'm losing it. You guys are driving me crazy. No, I'm driving myself crazy. I signed up for this. Not this. I mean, like my life. I like this. This is fun. The rest of my life, not so fun. Okay, so PCl5 times the molar mass of PCl5. Phosphorus, what did we say was 31 plus 5 times 35.45. That gives me 208. 208 times 0.052 moles, which gives me 10.8 grams PCl5. So that is the theoretical yield based on the limiting reactant. Oh, Josh, you're actually taking your science elective. Wow. And you don't even get paid. Damn. The rest of you guys have to take it. But I'm happy that you're here, so I hope you don't quit. Wait, you guys choose your classes? Well, freshmen, you guys don't choose your classes, right? Yeah, the first semester you don't, usually. But if you're older, you do, like next semester, you pick your classes. But for the first year or two, it's pretty regimented based on your curriculum. But then after that, you can just, oh, this elective looks cool, this thing looks cool. Yeah, you can, it's fun after that. Okay, cool. So now we have this as our total, as our theoretical. So we can divide our, remember this 3.64 that we had here? This is the amount of product that is produced from the person completing the reaction. So it's our actual yield. 3.64 divided by 10.8, and that's not very high. That's a 33.7% yield. So the answer is 33.7%. All right. Whew. So any thoughts or questions on that procedure? If that seems good to you, then you're good to go. Like the homework is gonna be a lot of repetition of this, but it's pretty straightforward if you just keep doing it. There won't be too many tricks. Unless they give you a tough balancing one, which throws that into the mix, but the math is all the same. Okay, next we'll move on to oxidation reduction. Think about this. Nah, you're good. No too much thinking today. Okay, so do you want to take a break or no? Yeah? No? Let's see what everyone online wants to say. Do you want to take like a 5-minute break online? Hal says yes. Lewis says yes. Zoe says, okay, yep, we'll take a 5-minute break. Snack time. Boom. Bahilma, perfect. All right, snack time. 7:39. I'll give you 6 minutes. 7:39, I will start again. We're making good time, so it's okay. Victoria just joined us again. Where were you?
I had to check the ambulance because we're having some issues.
Oh no, that's not good. What kind of issues?
There's no EMT on board, so we're trying to like find an EMT, and also I
big issue.
Some of the equipment.
Okay, well, if you have to go anytime, you can feel free to go. You don't even have to. You could email me later, like tomorrow, and tell me you got to leave. It's okay.
I was gonna say, do you have office hours on Thursday?
Hell yeah, 3 to 6.
Oh really? Okay, I'm gonna stop by because I gotta fix this.
Yeah, go do your thing. It's more important.
Okay, thank you. Have a good night.
No problem. Have a good night. Be safe. She specifically told the registrar, don't sign me up for Monday classes because I'm doing she drives an ambulance like at this time at night. So what they do, they signed her up for Monday night class. So. Oh, Dwayne, I'll add your attendance. Well, I'll make you late because you were late. So you get something. Yep, it's better than not being here at all. So that's good. I'm really hungry. And the Yankees are playing. So I'm gonna go home, and I think it was Josh who said you're heating up chicken tenders. That's like, I hit the spot. I hit my soul when you said that. Oh, that was Josh. I'm gonna do that. Okay, let's start up again. So, oxidation reduction. So what does that mean? So that means you have I should bring pre-made snack. You're right. I just didn't come prepared today. A busy day. So start now. Action. Oxidation reduction. What does that mean? So they call it redox, and it basically means there's two things happening at the same time in this reaction type. It involves a transfer of electrons, whereas the other reactions we talked about, and we didn't really cover in specifics any reactions yet, but things that we've seen ions, we've seen ionic compounds, and maybe we've seen them react a couple of times, but in those kind of reactions, the cations and anions switch. That's called a displacement reaction. In acid-base, it's kind of the same thing. They switch. But there's no transferring of electrons, meaning the charges of all of the atoms are the same in the before, in the reactants, and in the product. In oxidation reduction, that's not true. The charges, or I call them kind of pseudo charges, and we're going to be learning what that means. Is basically the term is the oxidation state, meaning the charge, I'll put quotes, the quote charge of the atom, how it changes from the left to the right side of the equation. So some examples of these redox reactions, the ones that have a changing in charge of each of the elements going from the left to the right side of the table, or right of the reaction: combustion, oxidation, well, obviously oxidation, right? So that includes tarnishing, rusting, different things like that. So those are the main types that involve this process. So let's continue and learn about them. So here's one. You have sodium and chlorine go together to make sodium chloride. This is an oxidation reduction reaction. And we'll learn how do we figure that out. That's what we're going to learn next. And here's exactly how. So the way to do that is we're going to assign these charges, or what we call as oxidation states, to these elements. An oxidation state is basically this, I don't know, I just said it twice, the pseudo charge. Let's just call it that and move on. Now, there's certain rules. We'll go over the first one. If an atom is in its elemental form, that means its oxidation state is 0. It's not reacting with anything. It's no need for it to have a charge. It doesn't have a charge. It's just a solid object by itself that is its elemental form. Elemental forms include things that are in their solid form, like solid iron, solid sodium, solid any metal, magnesium. It could include diatomic gases or triatomic gases that are in their elemental form, like O2 and O3, N2, H2, things like that. Those are considered in their elemental form. Also includes like liquids, like mercury is the only element that at room temperature is a liquid. So that would have a 0 charge, a 0 oxidation state. Then we have monatomic ions have the same oxidation state as their charge. So that just means the ions that we're used to, the 1A, the 2A, the 3A, the 7A halogens, the 6A, well, sulfur changes, but oxygen's always -2. Nitrogen and phosphorus do change, but at least for the metals, the 1A and 2A, they're +1, they're +2, the same as they always were. Transition metals are weird. They could be a lot of different things, as we know. Same for oxidation states. And the nonmetals, the halogens are usually -1. Oxygen's always -2. And then everything else from there actually it could be wonky. Like sulfur could be plus or minus, or carbon could be +4 or -4 or -2. It really depends. That's why I call it a pseudo charge. It really depends on what it's bound to in the reaction. So Other rule, fluorine is always -1. That should make sense because it's a halogen. Oxygen is always -2, except when it is in a peroxide. Now, what the hell is a peroxide? So the easiest peroxide to know is hydrogen peroxide, which you use like topical hydrogen peroxide. That is H2O2. So peroxides usually have the same amount of hydrogens as they do oxygens. They might have other stuff in there too, but you'll know, and I don't think you might, just know that rule. If one presents itself that's not hydrogen peroxide, so hydrogen peroxide is H2O2. That's the most common peroxide. If one presents itself that is not hydrogen peroxide, they'll tell you H3CO4 is blank peroxide. That would tell you, oh, that means the oxygen in this case is -1. So you don't need to memorize. I don't even know many peroxides name. I never need to do it in research. So, but there's abundance of them. So besides that, oxygen is always -2, as we know. And also hydrogen is always +1, just like we know on the periodic table from when it becomes an ion. So there's that. Okay, then everything else can be deduced from this information. So let's figure that out. Let's do some, it's actually really fun. It's like a puzzle figuring these out. So let's assign oxidation states. Here we go. Let's assign oxidation states to all atoms in the following. These are so much fun. So CO2. Oh, wait, we have a message. Oh, it's cool. You're good, Classen. So CO2. Oxygen is -2. So we have, here's the way I like to do it. I go like this. I draw arrows underneath, and I go -2. I write the oxidation state for the element, not for the total of them. Since there's 2 of them, you're going to have -4. And then that means, what's carbon? +4. So this kind of smacks in the face everything you learned about charges and ionic bonds and covalent bonds. Because like, whoa, we're dealing with, this is covalent, we're dealing with charges now, what the hell? That's why it's like a pseudo charge. It's not, it's just an oxidation state, it's just state. So don't get too focused on it. So you can deduce the information. Of course, they all equal 0, just like ionic bonds do with the pluses and minuses added up, unless it tells you otherwise. And in B, it tells you otherwise. It tells you that the complex of NO3 is -1. This means we can just write this information here. O is always -2. And then we can use that to figure, and use the minus sign to figure out what's nitrogen. And you can even set up a little equation if it gets complicated. You could say nitrogen plus 3 times -2 equals -1. Nitrogen plus, or nitrogen -6 equals -1. Plus 6, plus 6, nitrogen equals 5. Ta-da. So in this case, nitrogen is +5. You could think about this in your head as well, because I'm sure this is not too bad for most of you. So you have -6 from the oxygen. You know that total, it has to equal -1. That means the remainder is +5. +5 minus 6 is -1. Easy enough? It doesn't get much harder than that. So we'll do more. Do more practice. Wait, I'm going to do this. Okay. All right. So this is what you're going to get. This is more involved. So here's what I'm going to do. I want to show you the answers. Close your eyes. Keep them closed. 1 second. 1 second. Open them. Nice. Well, at home, like, I'm not closing my eyes. I'm eating my chicken tenders. That's good. That's good too. All right. So let's do these. So CHEM-125. All right. So what do we know? Someone tell me. What do we know? Perfect. Great place to start. O is -2. What else do we know? Good. K is +1. It's a group 1A. So now we can deduce the manganese from it. So you have potassium is +1, plus manganese plus 4 times -2 equals 0, since there's no net charge on this. So you have -8 plus manganese plus 1. So this, you do the stuff, and you figure out that if you do the stuff, and you figure out manganese has to be +7. Oh, Mn. So manganese is +7. So yeah, that's basically it for assigning oxidation states. So we'll do B together, and then I'll give you a minute to do C and D on your own. So for B, same thing. We have hydrogen this time. So we know hydrogen is what? Good, +1. Oxygen is -2. Good. Sodium is good, +1. And then iron, we don't know. We'll figure it out. So it turns out, so if you remember hydroxide is a -1 charge. And it turns out hydroxide's oxidation state is also -1 because it's composed of 1 oxygen and 1 hydrogen. When you add those up, -2 and +1, you get -1. So you have -1 in this hydroxide packet times 6 of them. So -6 plus the sodium, which is +4. And then that remainder is -2. So to cancel that out, you need a +2. This would be whatever these charges are, plus the charge, or the formal charge, not formal charge, plus the oxidation state of iron equals 0. So if you do this math, Fe equals +2. Like that. So another rule of thumb, well, not really a thumb, but never seen it. I've never seen a metal have a negative oxidation state, so they don't. But non-metals could have positive or negative. So keep that in mind. Okay, so I'm going to give you a minute or two to do C and D on your own, and then we will continue. And we'll go over them and then continue. Okay, so let's do the first one. This one's kind of difficult because you have to realize what it is. Now, NH4, we know from polyatomic ions, is ammonium. So ammonium has a +1 charge. So to figure out the formal charge of nitrogen in ammonium, you write NH4 +1. So if that's the case, then nitrogen has to be, if hydrogen is +1, then nitrogen has to be 1 less than 4, so it has to be 3. So since -3 + 4 equals +1 as the total charge of ammonium, nitrogen has to be -3. So that's one way you can get hydrogen as nitrogen as -3, is by looking at it that way. And also we know, obviously, that oxygen is -2, all the hydrogens are +1, and the only thing we have left over is phosphorus, which you can look at it as the whole, now that we have nitrogen, you can look at it as the whole compound of ammonium, this is called ammonium hydrogen phosphate. Or you can look at hydrogen phosphate individually and know it has a -2 charge. So hydrogen phosphate, HPO4 2-, and you can break it down by oxidation state here. So +1 for the hydrogen, plus P for the phosphorus, because we don't know, +4 times -2 for the oxygen. So you have -8 plus phosphorus plus 1 equals -2. So then this gets to 6 -1, 5. So phosphorus in this case is +5. -5. +5. +5 is +5. So another thing about nitrogen and phosphorus, they're either going to be ±3 or 5 a lot of the times. So if you see that, you're probably right. There's no rule whether it's positive or negative, but usually depends on either if it's with, it's positive if it's with more negatives like oxygen, and it's negative if it's with more hydrogens. So usually 3 or 5. Okay, cool. So hopefully that makes sense. Let's move on. Now, in a reaction, we didn't really talk about reactions yet, but you can figure out the oxidation state, just like we've been doing, of every compound in the reaction. And you can see if the oxidation state of, let's say, oxygen is changing from the left to the right side. This changing tells you whether the number of oxidation state is going up or down. It tells you, is the atom being, or is the element being oxidized or reduced? So here's where this comes into play. This thing maybe you've heard from high school called oil rig, this acronym, oil rig. The oil rig stands for oxidation is losing, meaning electrons. We're losing electrons. So oxidation is losing electrons. Electrons. Rig, reduction is gaining electrons. So if you're losing electrons, what happens to your charge? It goes up, right? So it goes up. Same thing with oxidation state. The oxidation state goes up if you're being oxidized. That makes sense, right? Why would they call it oxidation state otherwise? Yeah, that's true. So if you see that carbon's oxidation state went from 2 to 4, that means carbon is being oxidized in a reaction. And then something else has to be reduced. In any redox reaction, there's always both taking place, because you can't just spontaneously lose electrons out of nowhere or gain them out of nowhere. So it has to be transferred to some other atom. And so rig is reduction is gaining of electrons. If you're gaining electrons, your oxidation state or your charge goes down. So reduction means the reducing of the oxidation number, meaning the number goes down. That's the easiest way to remember it. Oxidation, positive, going up. Reduction, reducing the number, decreasing it. Then it gets more complicated. If something is being oxidized, you can refer to it as a reducing agent. And that's something that we, in chemistry and in biology, we like to talk about a lot. We talk about oxidizing agents and reducing agents to either help remove or add hydrogens to a certain compound that we want to protonate or do other things with it, give it a certain charge, whatever the case may be, or to break bonds or make more bonds, or give a compound the potential to partake in a specific type of bond, such as a disulfide bridge in proteins, which needs to be completely oxidized for that. So, and we can break those bonds by putting in a reducing agent, and it snips them, and then the proteins are free. So, anyway, if something itself is oxidized, that means it is losing electrons. It is gaining oxidation state, but it is also the reducing agent, meaning it is the agent, the secret agent, that goes in there and facilitates the reducing of whatever is being reduced. Kind of like an ionic bond, where like the sodium and the chlorine, they transfer the electron. The sodium's like, here, I don't want it anyway, you can take it. And fluorine's like, oh, I need one, I'll take it anyway. It's kind of a very seamless transfer. One is facilitating the giving, the other one is facilitating the taking. So that's why we get these terms, that's where we get these terms from. So it's a reducing, if something's being oxidized, it is the reducing agent. So it is facilitating the reduction of whatever is being reduced by giving it the electron that is reducing with. And then for reduction, same thing. In this case, we're decreasing oxidation state and we're gaining electrons. Oil rig, reduction is gaining. So we're gaining electrons. And what that means is we are called an oxidizing agent. We are facilitating whatever is being oxidized to give its electrons to me, since I'm being reduced. So us facilitating that makes us an oxidizing agent. So they go hand in hand. So that's the good thing. So the steps of what we're going to do in these questions is something like this. This would be an example on a quiz or a test or homework. Is in this reaction, obviously first thing would be balance it. Second thing would be name the oxidation states of every element in the product and reactant. Tell me which one's being reduced, which one's being oxidized, which one's the reducing agent, which one's the oxidizing agent. So big question. So we can do that. And I'll show you how I organize. It's a lot of stuff to write. So I'll show you a way I came up with organizing it very nicely. Okay, so first, I draw arrows just like I did before, going through the equation, and looking at the oxidation states. So oxygen, -2. What's lead in this case? Good, +2. Oxygen again, look at that, -2. What's carbon? Good, +2. What's Pb? Good, 0 by itself, elemental form, 0. Automatically something changed, so Pb went down, that means something else is going to change. Oxygen here, -2. What's carbon? Good, +4, because there's 2 -2s for the oxygen, +4 has to negate it. That was easy. We just figured out all of the oxidation states for every element in their products and the reactant side. The next step is we're going to draw a bracket, or 2 brackets. The first bracket is going to be between the thing that was either one of the things that's changed, and the other thing that's changed is going to be the second bracket. So we'll go from lead all the way to lead, draw a bracket. So we can see lead went from 2 to 0. Was it oxidized or reduced? So reduced. So reducing is gaining electrons. Oxidation state decreases. So yeah, if you weren't right with the first one, it's the second one. But yeah, so good job. So it's reduced. So we write reduced. Okay, so it's reduced. And now also that means by default, it happens to be the oxidizing agent. So that's just the definition. Whatever's being reduced, oxidizing agent. Whatever's being oxidized, reducing agent. So now we can do the same thing. I'll change the color. Well, I can change the color. Nice. Oh, I'll do this. What is this? Galaxy. All right, so it's pretty cool. All right, so carbon. Carbon's the other thing that's changed. So we'll draw a bracket in this cool hip color. Nice. So carbon was changed from +2 to +4. The oxidation state increased. Therefore, it is oxidized. Oh, what happened? I ran out of sparkly ink. There you go. Oxidized. And therefore, it is the reducing agent. Cool. So that's it. That whole process is really all you need to know about redox reactions and how that works. So are there any questions on that part? We're not done yet, but any questions on that? No? All right, cool. So there's the solution. Nice. Okay, we'll do another example. So what are the oxidation numbers of carbon in CO2 and CO3 2- respectively? So basically, find it out for each one. Let's change the color. Let's do something else that's cool. What do we got here? Gold. Cool. All right, so oxygen here, -2. Carbon, we just did this one, +4, because there's 2 -2s, +4. So we know that it's either going to be B or E. Now let's look at CO3 2-. In this case, we have a -2 charge as the total charge. We also have 3 oxygens this time. So -2, there's still going to be -2, but -2 times 3 equals -6. And we need to add whatever carbon is to -6 to make it -2. So what would that be? Good, yeah, still 4, +4 again. So the answer is B. So we'll put that in bronze. The answer is B, not E. Oh, wow. I mean the opposite of what I just said. Cool. All right, so we'll do not B, but E. Nice. Okay. Nice, good. There's more examples. Oh, classify the following. Yeah, let's do that. Oh, question. Oh, it's okay. All right, so last one, and then we'll talk about chapter 5 for like 10 minutes or so, and then we'll get going. And also, another thing is, well, I'll ask after the video. Okay, so this equation, is it a precipitation, which we didn't really learn yet, so it's probably not the answer. Acid base, we know. Oxidation, we know. And combustion, we know. So is it combustion? No. Okay. Is it acid base? No, but you thought about it because it has an acid in it, but it doesn't have a base, so no. For what? Or what? True, or water, or salt, or it does have a salt, but it doesn't have water. Okay, so it's oxidation reduction, whatever. That's what we're learning. What was that? Yes. Oh wait, am I stupid? So I like that thought. Now, precipitation reaction we didn't really talk about. So what that means is basically you have one or more ionic compounds that switch their cations and anions to create something that's insoluble, meaning it precipitates. And we'll learn about that specifically in later chapters. Now, for it to precipitate, that means it is an insoluble salt. Magnesium chloride is pretty soluble. So that is a little bit beyond this chapter. But so to be specific, it's oxidation reduction, but it's also considered a single replacement reaction because you replace the hydrogen from the HCl with magnesium. Good thought, good thought. So we're doing redox, so it's redox. Magnesium, let's do oxidation states just for the hell of it. Magnesium, what's the oxidation state? Good, 0. Cl, what is it? -1, and hydrogen, +1. Nice. Cl, what is it? -1. Magnesium, what is it? +2. Aha. And what's hydrogen now? +0. Yeah, +0. So it's 0. So it changes. So hydrogen changes from 1 to 0, which means it's reduced. Number goes down, reduced. And then magnesium goes from 0, oh, that's weird, 0 to +2. Therefore, it's oxidized. Okay, good. Any other questions on that? No? All right, cool. So we're going to conclude. Oh, wait, someone has a chat. Oh, no. So, Josh, to answer your question, it's not an acid, not because it doesn't have AQ. Oh, no, it is an acid. HCl, it is an acid here, but it's not reacting with a base, so we can't say it's an acid-base reaction. Since magnesium is just, it's reacting with magnesium metal and deteriorating it, oxidizing it to make it magnesium chloride. So, yeah. Okay, so I'm going to end the video. Stop recording. I do a lot of editing.